Here we've got the notes for section 3.2, which deals with differentiability. So our objectives, find where a function is not differentiable, distinguish between corners, cusps, discontinuities, and vertical angles. See how differentiability implies continuity, and then approximate derivatives numerically and graphically. Okay, so these four cases, see if I can get them all on here, are when you do not have a derivative at some value. So if you have a corner, there is no derivative. That's because the derivative from the left and the derivative from the right are not equal. This one is -1, that one's +1. A vertical tangent doesn't exist because remember, derivatives measure the slope. So when the tangent goes vertical, it's undefined. So if the slope is not defined, the derivative is not defined. Cusp, simply for the same reason as corner, from the left and from the right, you get different slopes. Same thing on discontinuity. This has a slope of -1, that has a slope of +1. Oh, sorry, not that. If there's a break in the graph, I was talking about this like it was a slope equation. You can't have a derivative here because at the endpoints, you have any number of derivatives. Same thing kind of here. There's any number of tangent lines I can draw. Okay, so example 1 here, find all points in the domain of f of x equals the absolute value of x minus 2 plus 3, where f is not differentiable. So we need to look at the graph of that guy. So let's see here. Delete that out of there. So option number absolute value of x minus 2 plus 3. Draw. Uh-oh. Zoom out. See if I can find it. Oh, zoom out again. Hey, there it is. It's actually an absolute value function. That is. I wonder what my units are. View window. Standard. Draw. Hey, there we go. Over 2 and up 1, 2, 3. So it looks like this. So it is not differentiable where that corner is, and that corner lies at the point 2, 3. So that's where x is not, or the function is not differentiable, and it does lie in the domain. Okay, so here, differentiability implies local linearity. So it says here, differentiable functions are locally linear. That is a function that is differentiable at a closely resembles its own tangent line, very close to a. Just what that means is that if you have, even if it's a curve, if you zoom in enough, the section of the curve you're looking at will look like its own tangent line. Because it's the same way essentially computer screens and whatnot draw curves, is they actually just draw a series of straight lines that are so short that your eyeball can't tell the difference. So if you zoom in far enough on a curve, it looks like a straight line. For some curves you have to zoom in farther than others, but it still holds true. So your calculator can approximate ones by doing the numerical derivative, or sorry, not approximate, numerical derivatives for you to do, ender. So you're averaging two values that are finding the midpoint of two values that are very close together, 0.001 off of your value. So f of x, you can do the same thing if you just have variables. So we'll use these formulas down here. So example 2, if f of x equals x cubed, to approximate f prime of 2. So that's 2 is my a value. So if I'm going to use this. So f of a plus would be 2 plus 0.121 cubed. That's doing the add. Minus 2 minus 0.001 cubed all over 0.002. And those are all just calculator problems. So let's go to my calculator, and we'll do it all. 2 plus 0.001 cubed minus 2 minus 0.001 cubed divided by 0.002. So this comes out to be 12.12345 zeros and then a 1. So that's the numerical approximation for the derivative at 2. So down here at 0, so this would be the absolute value of 0 plus 0.001 minus the absolute value of 0 minus 0.001, all divided by 0.002. So my function is the absolute value, so this in here is the a plus 0.001, so this number here is my a. I'm plugging using this. So that's going to be 0.001 minus 0.001 divided by 0.002, because these are going to be the same number because it's the absolute value. So this thing comes out to be 0. Now just a note, that's actually the wrong answer, because for the absolute value function, there is no derivative when it's 0, so be careful with the numerical derivative. Okay, so here, so let f of x equals ln x, use ender to graph f prime of x. Can you guess which function this is by graphing? Okay, so what that's asking you to do is, so we don't have x, this can look a little weird on my calculator getting it typed in correctly. So it's going to be ln of x plus 0.001 minus, whoops, need an extra set of parentheses. Don't need that one, need one there. And then minus ln of x minus 0.001. So that's the top of the fraction. And then on the bottom, over 0.002. Draw. So we get this lovely shape. Did I do that right? Let me make sure, get my thing right. Yeah, okay. So this essentially is my curve that I get if I graph it. Can you guess what function this is by analyzing the graph? This is actually 1 over x, which means the derivative of the natural log function is 1 over x. Okay, so if f has a derivative at some value, then it's also continuous because you're essentially approximating with the line, so it has to exist there. Okay, and then we've got the intermediate value theorem. So it says if a and b are any 2 points in an interval in which f is differentiable, then f prime takes on every value between f prime a and f prime b. So does any function have the unit step function shown below as its derivative? So I need a function that has a slope of -1 left of 0 and a slope of +1 to the right of 0. That looks like this, which is the absolute value function. Technically, you could put a plus k out here, because if you move the graph up or down, it's not going to change anything. But the absolute value function has the unit step function as its own derivative. Which brings us to the end of section 2.